The history of chemotherapy is interesting, littered with a lot of important names, and I'm going to give you a little run through on the development of some of the agents currently used in treatment. Fritz Haber is a German industrial chemist who won the Nobel Prize in Chemistry in 1918 because he was the first one to figure out industrial production of ammonia, and ammonia became necessary in fertilizer, so it became a big deal in terms of widespread agricultural. But he was also a member of the German elite when World War I broke out, and he was tasked to develop other industrial compounds. And the first compound that he created was this, a sulfur-based compound, which was actually gaseous, and it was really to be used in chemical warfare against the Allies. And he created this compound. Remember this CCCl. And that's a gas. And it's a sulfur gas. And exposed to the air, it was yellow colored. So they called it mustard. And this was incorporated into bombs, and these bombs were dropped. And this material is extremely irritating to skin, eyes, nasal membranes, this mustard gas, and caused such profound irritation. If any of you have taken a deep whiff of ammonia, you'd know how caustic some gases are, and would cause enough irritation to cause profound lung inflammation and death. But there were recruits, military recruits, who actually survived that initial attack, only to die 2 to 3 weeks later, either of infection or profound bleeding. And at autopsy, military recruits, you do not require any written permission for an autopsy. Their bone marrows were completely empty. I mean, they were empty. It was a desert. And it was not understood exactly what was going on as to why the bone marrow was damaged. So the Department of War, over a period of 30 years, commissioned 2 famous pharmacologists, whose names were Goodman and Gilman, and 2 famous hematologists, whose names were Wintrobe and Damashek, to look for safer compounds. And these safe compounds that they developed was this. They replaced the sulfur with the nitrogen, which made it a crystalline powder instead of a gas, but it still had this key compound here. And what they did is they called this nitrogen mustard, and it was a crystalline compound, and they treated patients with cancer because of its ability to damage the bone marrow. In their 1946 Journal of the American Medical Association article, they showed people with what in those days called lymphosarcoma, today we call lymphoma, big tumors in the neck just shrank to nothing. Not permanent reductions, but significant reductions in the size of the tumors. Now, actually, they were ready to publish this in 1942, but we were engaged in another war, and so the Department of War prohibited them from publishing the research, and it first appeared in the Journal of the American Medical Association in 1948, well after the war. And this nitrogen mustard compound, which was really just mustard gas in crystalline form, was found to do the following. DNA is a double helix. It's actually a ladder that you wind this way, and it spirals up. And if you unwind the ladder, it looks like this. And what happens is that this ladder unzips in order to allow cell division to occur. And what they found is that nitrogen mustard, this CCNCC, would bind the 2 sides of the DNA, stop them from unzipping, the cell won't divide, and a cell that can't divide dies. And what they did, this technical term for carbon is called an alkyl group, and so this was referred to as the first alkylating agent to prevent the division of DNA, but it's hard to work with. It's given intravenously, and if it leaks out of the vein, it burns a hole in your hand. And so it was very, very toxic, and it had to be reconstituted in fluid, so they kept looking, scientists, for simpler compounds that they could use to safely administer it. So what they did is they tried to look at ways to make it easier to incorporate. So they took the amino acid aniline, and they combined it with a benzene group. Don't worry about this. I'm just doing this for my own edification. And combined it with that thing that you've been seeing, this alkylating agent, the thing that was found in nitrogen mustard. And what they created was L-phenylalanine mustard, or LPAM, which we call today melphalan or Alkeran. And that was actually created by the Russians, but was first used in the United States and Canada by Bergsagel, Alexanian, and Kyle to treat patients with all types of cancer, but this was the first agent used in multiple myeloma. Meanwhile, at the Mayo Clinic in 1948, a PhD chemist called Hench was doing investigations on pig adrenal glands. Exciting, I know. And the adrenal gland has two separate parts. There's a thin outer shell called the adrenal cortex and a central component called the adrenal medulla. Adrenal medulla is bigger, so it was easier to investigate. So already in the 20s, people extracted chemicals out of the adrenal medulla and found compounds that, because it came from the adrenal gland, got the trade name, not the generic name, chemical name, of adrenaline, from adrenal. So that had already been compounded out. About an hour from the Mayo Clinic was a meat packing plant run by Hormel Spam. So, just so you know. And at that time, the adrenal glands from the pigs were considered waste products. So they brought truckloads of adrenal glands to dump at the Mayo Clinic basement. I mean, thousands of adrenal glands, actually tens of thousands. And he worked to extract the different compounds from that thin little adrenal cortex. And he ended up calling it compound E, compound F, compound G. But he found they had profound anti-inflammatory properties. And so he worked with an arthritis doctor, a rheumatologist named Hench. And Hench took this compound F, which is what it was called at Mayo, and gave it to people with arthritis. And he's got black and white videotape showing people who were wheelchair bound from their arthritis climbing upstairs. And so he renamed compound F cortisone, and they took the Nobel Prize in 1952. Well, it wasn't long before it was thought that maybe this cortisone, maybe we could use that in cancer. And the first place where cortisone was used in the treatment of cancer was by Sidney Farber. Those of you who've ever been to Boston know about the Dana-Farber Cancer Institute. And Sidney was a pediatric hematologist. He was treating childhood leukemia. And he took cortisone and gave it to children with childhood leukemia and showed really quite rather impressive benefits. It was really kind of exciting. And once it was demonstrated to be useful in leukemia, it started to be applied in a lot of different cancers, including multiple myeloma. A more potent form of cortisone was developed. It was called prednisone, but chemically it's almost completely identical. And quite frankly, melphalan or Alkeran is nothing but mustard gas in a pill. And again, Keilberg, Sagel, and Alexanian administered this Alkeran and prednisone to patients with multiple myeloma, and patients who really had no treatment, lived less than a year, were now living 3 and 4 years. It was really quite remarkable. And so this brings us to the late 60s. But things stagnated at that point because the actual biology of multiple myeloma was simply not understood. Yes, there was subsequent development of more intense cortisone, so cortisone, prednisone, and then eventually your favorite, dexamethasone, incorporated. So that was really quite a useful compound. And then in 1975, McElwain and Powles in Great Britain said, well, if melphalan works in the treatment of multiple myeloma, what if we gave like a rockin' big dose of melphalan, a really high dose? And they did that in 8 patients with multiple myeloma, and it actually resulted in favorable results, even in patients who had failed regular doses of melphalan or Alkeran. Unfortunately, with that treatment, their normal blood counts were really destroyed, and it took 6 weeks, 8 weeks for the blood counts to recover. And so these patients had all kinds of problems in terms of transfusional support. Mid-70s, platelets were not a very common available. Pheresis didn't exist. And so patients succumbed to that, but it was highly effective. It was subsequently determined, based on the studies done by E. Donald Thomas, who won the Nobel Prize in Medicine for bone marrow transplantation, that if you took bone marrow out first, held it, gave the chemo, then gave the bone marrow back, transplanting it, you could shorten the recovery time of the blood counts to 10, 11 days. And so that really started the second piece, which was high-dose melphalan with rescue with stem cells, with seeds to reseed the garden. But then things really, really stagnated until about 1998, 1999. Literally nothing happened for 24 years. It was at that time that there was this interest in the scientific concept of angiogenesis, the ability of cancerous tumors to actually stimulate blood vessel growth into themselves so that they could be fed and grow even further. In the mid-50s, thalidomide was developed as an oral drug to treat the nausea and vomiting of pregnancy. This drug was distributed in Australia, New Zealand, Canada, and Europe. And the most severe vomiting in pregnancy would occur in the first trimester. So that's when you'd give the thalidomide, during that first trimester. Now, during the preliminary testing in the 50s, the FDA found that thalidomide caused nerve damage in the feet, what we refer to as peripheral neuropathy. It would basically cause numb, burning feet. And so the FDA, which in the 50s was an incredibly, incredibly weak organization, minimally involved in the approval of medications, said no thalidomide in the United States. Too dangerous because of burning feet. And then within 3 years, the profound birth defects started showing up. Children born without arms, children born without legs, which led to the complete shutdown of thalidomide use by 1958. Thalidomide was revived because it turned out that it was useful in the treatment of the skin complications of leprosy. Okay, not a big market, I'll give you, but it was approved and available for those skin complications of leprosy. Fast forward to 1998, and some basic research had suggested that thalidomide was useful in the blockade of those blood vessels, that angiogenesis to feed tumors. And so at that time and today, there's an enormous myeloma center in Little Rock, Arkansas, which at the time was headed by an Austrian physician named Bartel Barlogi, and a wife of a cardiologist with multiple myeloma came to him and said, this thalidomide, it blocks angiogenesis. We should test it in multiple myeloma. And Bartel was a definitely out-of-the-box thinker and thought, this is actually not a bad idea. And so he did it in the cardiologist. The cardiologist failed and died. And the second patient was treated, had multiple myeloma with a quantitative immunoglobulin protein of 4,000, began thalidomide, and within a month it was 100. So this was presented at the American Society of Hematology in 1999, and honest to God, I was in the audience and I said, that can't even be true. It's so amazing. Too good to be true. But it was true, and that really ushered in that next generation. And no one here takes thalidomide, but I'll tell you, all you have to do is tweak one methyl atom to an amino atom in thalidomide, and you get lenalidomide or Revlimid, and you add another methyl group, and you get pomalidomide or Pomalyst, and I suspect everyone in the room has taken those medicines. But of course, they never shed the legacy of thalidomide and the birth defects. So every month, you have to call and discuss very detailed, intimate details of your sex life and your contraception, and guarantee that you're not going to get pregnant and that you're not having relations with anybody who could get you pregnant, all related to that thalidomide birth defect. 2004, a relatively obscure scientist named Robert Orlowski was working in his laboratory at the University of South Carolina when Takeda Pharmaceuticals came to him and said, we want you to test a compound. The cells in the body have garbage disposals. You have to have that. You've got to get rid of the waste products. And the garbage disposal of the cell is called the proteasome. And Takeda had developed a compound, bortezomib, that actually blocked the garbage disposal. And once that happened, all the garbage would build up in the cell and kill the cell. So he asked Orlowski to look at this, and he tested it in lung cancer, colon cancer, breast cancer, pancreas, prostate, but he also tested it in 4 myeloma patients. And all 4 of those myeloma patients had a very, very dramatic response. Takeda said, okay, this is good, we're going to go forward with it. They gave it the brand name Velcade and said, we're off to the races. And that really ushers in the novel agent era of multiple myeloma. And then Orlowski, after that discovery, became the head of the myeloma program at MD Anderson. One of the things as the research moved, it was to recognize unique proteins that identify cells. Every cell in the body has unique proteins on its surface. We call them antigens, doesn't matter. They're just proteins on the surface. And you're like, I don't know any of these proteins on the surface. But actually, time for a quiz. You can identify a cell based on the protein on its surface. So if I told you that a certain cell had protein A on it, and that identified the cell, could you identify what cell that is? Okay. Some of the cells actually have protein B. or protein A. Anyone identify the cell yet? No. Some patients, not patients, all of us, have both proteins on the surface. So we're antigen AB. Anyone? I can't hear you. Red blood cells. So red blood cells, if you have neither one, it's O. Karl Landsteiner, who won the Nobel Prize in 1902 in medicine, had recognized that these cells, red blood cells, had different proteins on the surface. But of course, it's 1902. Nobody knows from antigens, so he called them types instead of antigens. But it's still the same thing, unique proteins that identify cells. And so research started to begin about these specific proteins on the cell surface. And so the first one to be attacked was a protein. They started looking at myeloma cells, what's unique. And cells, the terminology uses this CD or cluster designation. And these cluster designations really are assigned arbitrarily. This is a T cell. This is a suppressor T cell. This is a stem cell. But what was important for us is this. CD38 and CD138, those are plasma cells. And those were found on the surface. And so then the question is, can we produce an antibody, the proteins that help fight infection? You get antibodies when you get your flu shot and your COVID shot and your tetanus shot, or you step on a stone and you get immunized and you develop antibodies. Can we develop antibodies to these myeloma proteins? And it turned out that by this time, monoclonal protein production technology, so-called hybridomer technology, allowed infinite production of antibody proteins. And so these antibody proteins, anti-CD38, anti the protein on the myeloma cell surface, was identified, and two were developed, one called daratumumab, or Darzalex, and the other called isatuximab. What's the trade name for isatuximab? Sarclisa, thank you. And so that ushered in the next first targeted immune therapy based on recognizing these unique antigens. And finally, and that's going to be summarized by Professor Zonder, is the identification of, no, I don't like that, BCMA, or B-cell maturation antigen, also unimportant to know. But antibodies can be developed to these proteins, and those become the targets both for CAR T, which he'll explain, as well as bispecific antibodies. So the development of chemotherapy for multiple myeloma, past, present, future, is very, very exciting. I actually, before I came down, I looked in our bone marrow transplant database. And again, this goes back a long way before a lot of these things were introduced. But when I looked, we have 31 patients who survived over 20 years after their transplant with multiple myeloma. So 20 years ago, it was 2004. It's just at the fringe of the first development of Velcade, Revlimid, bortezomib, and lenalidomide. We have 147 15-year survivors, and we have 549 10-year survivors. And at the rate that new agents are being, at the rate in which new products are being developed, new structures, new variations on CAR T, CAR NK, bispecifics, trispecifics, different antigen targets on the plasma cell, things really, really look bright for our myeloma patients. So this has become a disease where really you're entitled to have an enormous amount of optimism going forward in terms of what you can expect in terms of good outcomes. I've had patients that I've cared for well over 20 years where things kind of stopped working. Then there was a new discovery and a new innovation, and we instituted that. And if that became exhausted, something new came along, because things are being developed now and approved like every single year at the rate we're going. I mean, we now have 3 approved anti-BCMA antibodies. We have 1 approved G6PR5D, I don't know, antibody, with more on the horizon. And so with that little background, I'll yield the podium. Thank you.